The last part of Chapter 2 introduces Avogadro's number and the mole. It's typically a topic that scares many in chemistry, but it really isn't anything uh, to worry about. And once we look at it, you'll kind of see that really it's pretty easy to understand what a mole represents. Right, so it's easy to understand what a mole represents because we understand what one pair means. We know if I said I had a pair of socks, that I'm talking about 2 socks. Or a dozen. If I said I had a dozen eggs, we would know that we're talking about 12 eggs. Or a dozen cookies would be 12 cookies. And I could also say I have 3 dozen cookies. And we'd all know that 3 times 12 is 36, so 3 dozen would be 36 cookies. Well, a mole represents the same thing, except for on a much larger scale. So when I say I have a mole of something, I'm saying I have 6.02 times 10 to the 23 of that thing, right? A giant number. But I'm talking about atoms or molecules, and I'm using a mole because it's basically the chemist's way of taking really large numbers and turning them into smaller numbers that are easier to work with. So instead of saying I have 6.02 times 10 to the 23 atoms, I would say I have a 1 mole of that sample. In the same way, I can go from 1 dozen to 3 dozen. I could go from 1 mole to 3 moles and simply just multiply that number by 3 and come up with 18.06 times 10 to the 23 atoms or molecules. And again, it's hard to think about something that size because we don't work on that scale, we don't live on that scale, right? This is a giant number, but atoms and molecules are very small, and so in a sample, right, it's typical that I'd have a very large number of atoms or molecules. So this number is so large that if we could count 10 million molecules a second, right, it would take us 2 billion years to count 1 mole. So a mole, it's defined as the quantity of a sample that contains the same number of atoms or molecules as a 12-gram sample of carbon-12. And again, it's nothing to be confused by, right? It's simply just a chemist's way of taking a very large number of atoms or molecules and turning it into a number that's much easier to work with. And as we'll see a little bit later on, we can also use that quantity to relate the different masses of different compounds and different elements with each other. And so it's easier to think about a reaction in terms of 1 mole of this or 2 moles of this as opposed to how many molecules do I have present or how many atoms do I have present in that reaction. So let's just take a look at what a mole represents, right? And it's very important to pay attention to what you're being asked in these questions when we're being asked about a mole of something. Are we being asked for a mole of atoms or a mole of molecules? And so in this first example, if you have 1 mole of oxygen atoms, right, I would have 6.02 times 10 to the 23 oxygen atoms. If I had 1 mole of oxygen molecules, well then I'm talking about O2, which is a molecule of oxygen, right? 2 oxygen atoms bonded together. 1 mole of oxygen molecules would still contain 6.02 times 10 to the 23, but it's no longer atoms I'm talking about molecules. And so this is an important distinction, whether we're talking about atoms or molecules. So in this case, right, 1 mole of oxygen atoms, 6.02 times 10 to the 23. 1 mole of oxygen molecules, O2, well, I'd have 6.02 times 10 to the 23 oxygen molecules. Now here is the difference. Within 1 mole of oxygen molecules, how many oxygen atoms do I have? So I have 1 mole of oxygen molecules. So I have 6.02 times 10 to the 23 oxygen molecules. I want to multiply by something that leaves me with atoms of oxygen. And I know that in every 1 oxygen molecule, I have 2 oxygen atoms. So I can multiply by 2, oxygen molecules cancel out, and I'm left with 1.2 times 10 to the 24 atoms of oxygen. So again, what you're being asked for is very important. Am I being asked for atoms? Am I being asked for molecules? So here's a question for you guys. How many sulfur atoms are present in 1 mole of aluminum sulfate? Do I have 1 sulfur atom, 3 sulfur atoms, 4 sulfur, 6.02 times 10 to the 23, or 1.8 times 10 to the 24? In taking a look at this problem, right, we can do the same calculation. I have 1 mole of aluminum sulfate. And if I want to break this down, right, I'm asked for sulfur atoms. The sulfur is in our sulfate, and so in 1 mole of aluminum sulfate, if I break this down, I have 2 moles of aluminum. That's what this subscript 2 means, and I'm going to have 3 moles of sulfate. And so if I have 3 moles of sulfate, each one of those sulfates has 1 sulfur atom. So I have 3 moles of sulfate, SO4 2 minus. I know in each 1 mole of sulfate, I have 1 mole of sulfur. So moles of sulfate cancel out. So in 3 moles of sulfate, I have 3 moles of sulfur. And I know that in 1 mole of anything, right, whether it's sulfur or it's copper or it's carbon or it's aluminum, I would have 6.02 times 10 to the 23 atoms of sulfur. So again, moles of sulfur would cancel out. I'd multiply 3 by 6.02 times 10 to the 23 to come to a final answer of 1.8 times 10 to the 24 sulfur atoms. We need to pay attention to what we're being asked for in the question, right? We're being asked for atoms of sulfur, not moles of sulfur, not molecules of aluminum sulfate, right? We're being asked for moles of sulfur. So 1 mole is always 1 mole. It's always 6.02 times 10 to the 23. However, as we've looked at in chapter 2, we looked at the masses of different elements. Not all atoms or molecules weigh the same, right? The atomic weight of an element in AMU is equal to the mass in 1 gram of 1 mole of that substance. And that's where these variations come of how much of that material do I have. So for example, and this is from the definition of what 1 mole is, right? 1 mole represents 12 grams of carbon-12. So if I had 12 grams of carbon-12, I would have exactly 1 mole of that sample. So let's look at hydrogen, for example. Hydrogen on the periodic table equals 1 atomic mass unit. So if I had 1 gram of hydrogen, I would have 1 mole of hydrogen. So we can go directly from AMU on the periodic table to mass in grams of that sample that you would need to have 1 mole, right? 6.02 times 10 to the 23. The mass is going to change, right, because the atomic weight is going to change for each of these elements. Or if we're talking about a molecule, the molecular weight would change. So let's look at chlorine, for example, right? Equals 35.45 AMU. So if you had 35.45 grams of chlorine, you would have 1 mole of chlorine, the element. Silver, right? Look at the periodic table. Silver is 107.8 AMU. So if we had 107.8 grams of silver, you would have 1 mole of silver. So now we can go directly from the periodic table, we can go directly from the atomic weight to the mass of that sample we would need for an element. We could also go from the molecular weight for a compound, right, when we had multiple different elements present to find out, once I know that amount in AMU, I can go directly to that amount in grams. That's what I would need to have 1 mole of that sample. So let's just take a look at that, right? 1 mole of oxygen atoms. Well, oxygen is 16 AMU. So if I had 16 grams of oxygen, right, that would be 1 mole of oxygen. Now I had a mole of oxygen molecules, which is O2, meaning I have 2 oxygens present. So O2 is 32 AMU because I have 2 oxygens present. So to have a mole of oxygen molecules, I would need to have 32 grams of oxygen, right? And that would equal 1 mole of O2. Not to be confused with just an elemental oxygen. Now let's look at water, where we've mixed 2 different elements together. So hydrogen is 1 AMU, oxygen is 16 AMU. So 16 plus 2 is 18 AMU. So if I had 18 AMU of water, right, 1 mole of water, I would need to have 18 grams of water for 1 mole of that water. We can go directly from the periodic table, the atomic masses on that periodic table, to determine the mass in grams we would need to represent 1 mole of that sample. Right, and that gives us the molar mass when we're talking about compounds where we've put many different elements together. And so for the molar mass of a substance, it's the mass I would need to have 1 mole of that sample, right? And so again, the molar mass is the grams, right, you would need to have 1 mole of that sample. And that's equal to the formula weight in AMU. So again, we'd go to the periodic table of the elements and we'd look up, what is the weight of each of those. And so let's look at glucose, for example. Glucose is C6H12O6. So I have, right, within 1 mole of glucose, I would have 6 moles of carbon, I would have 12 moles of hydrogen, 6 moles of oxygen. And go to the periodic table, carbon is 12 AMU. We'll say hydrogen is approximately 1 AMU, and oxygen is approximately 16 AMU. So that means with the 6 moles of carbon there, I'd have approximately 72 atomic mass units of carbon represented. I'd have 12 AMU of hydrogen represented. And I'd have 96 AMU of oxygen. And if I add those all together, that would give me approximately 180 AMU for glucose. And what that means is I would need to have the same amount in grams for each of these. So 72 AMU of carbon would be 72 grams of carbon. 12 AMU of hydrogen, to represent 12 moles of hydrogen, would be 12 grams of hydrogen. 96 AMU would be 96 grams of oxygen. So if I add these together, I would have to have 180 grams of glucose to have 1 mole of glucose. We can break that down on an element by element basis, right? 6 carbons at 12 AMU each. So 6 times 12 is 72, 12 hydrogens at 1 AMU each, and then 6 oxygens at 16 AMU each, to see that the molar mass of glucose is 180 grams. That would represent 1 mole of glucose. Within that 1 mole, I'd have 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. And so here's the most important calculation we're going to see in this chapter, that we're going to see over and over and over again. You're going to use on a daily basis this semester, next semester in lab. And that's our molar calculation, how to determine how many moles I have in the sample. So moles equals the mass that we're talking about divided by either the atomic mass if it's an element or the molecular mass if it's a compound. And so we're going to use this calculation to determine how many moles I have in a sample. And so let's look at this calculation in an example here. A banana contains 0.545 grams of potassium, and I've given you the atomic weight of potassium. Potassium is 39.1 grams per mole. How many moles of potassium does this represent? So we can do this calculation two ways. We can do this calculation just looking at normal dimensional analysis. So I have 0.545 grams of potassium, right, where potassium is K, symbol K. And I know from the information given, my conversion factor, I know that for every 1 mole of potassium, I need to have 39.1 grams. That's this conversion factor right there. And I'm just using that conversion factor to go between grams of potassium and moles of potassium. So I'd see what I would need to do mathematically. I would need to divide 0.545 by 39.1 to see that I have approximately 1.39 e to the negative 2 moles of potassium. So that's doing the calculation with dimensional analysis. I could do the calculation using the equation as well, right? Moles of potassium equals the mass. Well, I've got 0.545 grams of potassium, and I know potassium is 39.1 grams per mole. We'll see we do the same operation. I divide the mass by the atomic weight, and I'm going to get the same answer, 1.39 e to the negative 2 moles of potassium. So you could do those calculations either way, whatever you feel more comfortable with for these calculations. So here's a sample calculation for you to try. A silver dollar weighs 26.73 grams. The atomic weight of silver is 107.8 grams per mole. Right? How many moles of silver does this represent? So by dimensional analysis again, we've got 26.73 grams of silver, and I know that in 1 mole of silver, I need to have 107.8 grams of silver. So again, we'll see by keeping track of our units, right? Grams of silver cancel out, and we're going to be left with moles of silver. And so when we work our way across, we're going to be left with 0.2480 moles of silver. Or in scientific notation, 2.480 e to the negative 1 moles of silver. We could do the calculation this way, or we could look at it using the equation of moles equals grams over molecular weight. I reported this answer to 4 significant figures because our measurement, right, we measured the mass of silver as 26.73 grams. So there's 4 significant figures there, so I'm going to report the final answer to 4 significant figures as well because I'm doing multiplication and division. So I'm going to go for the number that's least significant, and that's the number that we measured, the mass of that silver dollar. We can do that calculation another way too. So here is another sample question. There is 1.42 moles of fructose with a molecular weight of 180.2 grams per mole in 2 liters of Mountain Dew. This is a real calculation based on a real bottle of Mountain Dew. So if you're a big fan of soda, right, this is how much sugar is in a 2-liter bottle of soda. So let's do dimensional analysis. 1.42 moles. I want to multiply that number by something that gives me grams of fructose. So I want to cancel out moles, and I'm going to be left with grams of fructose. Well, I know from the molecular weight that in 1 mole of fructose, I would need to have 180.2 grams of fructose. So again, I multiply, and I'll see that moles cancel out, and I'm going to be left with units of grams of fructose. That's good. That's what we're looking for. Approximately 256 grams of fructose. Reporting the answer to 3 significant figures because there's 3 significant figures in our measured amount of 1.42 moles of fructose. And another thing to do that I haven't brought up before is we always want to check our calculation. We always want to check, does this number make sense? Well, 1 mole, if I had 1 mole, I should have 180 grams. I have a little over 1 mole. I have almost 1.5 moles. So yeah, I should have over 180 grams, and then half again would be another 90. So I should have somewhere close to 270 grams, right? If I had 1.5 moles, I've got a little bit less than 1.5. So yeah, I should be a little under 270 grams. I have 256. So yes, the calculation makes sense. Right, so we've just looked at grams to moles, moles to gram type calculation. We can also think about how many atoms or molecules are in that sample as well. And so we know, right, 1 mole is Avogadro's number, 6.02 times 10 to the 23 atoms or molecules. So if I had 1 mole of HCl, where HCl is a molecule, right, I would have 6.02 times 10 to the 23 HCl molecules. If I had 1 mole of iron, and iron being an element, right, I would have 6.02 times 10 to the 23 atoms of iron. So how would I go from grams to moles and moles to now atoms or molecules, depending on what I'm talking about? And so let's just use that previous calculation of moles in a silver dollar to think about that. I had, in that sample, 0.2480 moles of silver. So let's see. I have 2.480 moles of silver. I want to multiply by something that would leave me with, right, atoms of silver. What would that conversion factor be? How could I go from moles of silver to atoms of silver? Well, I know by Avogadro's number that in 1 mole of silver, I would need to have 6.02 times 10 to the 23 atoms of silver. And we'll look, right, moles of silver cancel out. That would leave us in units of atoms of silver, and that's good. That's what we're looking for. So multiply 0.2480 by 6.02 times 10 to the 23 to see that I would have approximately 1.493 times 10 to the 23 atoms of silver. Now we can go one step further. If I know moles of a sample, I can find mass. If I know mass, I can find moles. And from moles, I can also find atoms of that sample or molecules in that sample using these calculations. We can think of the formula, or we can also just think of dimensional analysis. How would I go from units of moles of silver into units of atoms of silver? Well, the conversion factor I know is Avogadro's number. Avogadro's number tells me that in 1 mole of anything, I would have 6.02 times 10 to the 23 of that sample. So here's a calculation for you guys to try. The average human body contains 4 grams of iron, where the atomic weight of iron is 55.8 grams per mole. How many atoms of iron does this represent? So there's going to be 2 steps to this calculation. The first step, right, I know I have 4 grams of iron. And I know that 1 mole of iron weighs 55.8 grams, right? My first conversion factor, I'm using the atomic weight of iron. Grams of iron will cancel out, and I'll find that I have approximately 0.07168 moles of iron. And in a case like this where we have multiple calculations, let's not round and worry about significant figures until we get to the last calculation. So I have this many moles of iron. Now I want to find out how many atoms of iron does that represent. So I've got 0.071685 moles of iron. I want to multiply by something that gives me atoms of iron. Right? And this is very similar to our last calculation where all I know in 1 mole of iron, I have 6.02 times 10 to the 23 atoms of iron. Just check our units, right? Moles of iron are going to cancel out. I'm going to multiply by Avogadro's number, 6.02 times 10 to the 23, to see that I have 4.3 times 10 to the 22 atoms of iron. 4.3 E22 atoms of iron. Just looking at the initial problem, 4 grams, let's say that was the measured number because we're getting the atomic weight from the periodic table. So we're going to say that's defined or a given number. So 4 grams has 2 significant figures as represented. So I'm going to report 2 significant figures in the final answer of 4.3 e to the 22 atoms of iron in that sample. So you should be very familiar with basically looking at this pathway, this process, and being able to start anywhere of this process. If you have grams of a sample, right, we can use the atomic or molecular weight, and that would give us moles in the sample. And then if I wanted to find out atoms or molecules, right, we need to use Avogadro's number. That would allow us to find atoms or molecules in the sample. So you should be able to start any step in this process. I could give you moles and ask you to find grams and work backwards. I could give you molecules and ask you to find moles or ask you to find grams. I could give you grams and ask you to find moles or atoms or molecules. So, right, these calculations work in both directions. And so here's just one more kind of question to think about and just work through more of just a problem of thinking about what we know and how we would do those calculations and what steps would be involved in something like this. We have 1 mole of quarters, and we want to determine how much that mole of quarters weighs, and we're given that each single quarter weighs 5.67 grams. And to give us one more step and one more practice with this, I added in, we want to convert that final weight from grams to kilograms. So first, I know each quarter is 5.6 grams per quarter. I have a mole of them. So I need to figure out how many quarters I have in a mole. So 1 mole of quarters, right, I would have in 1 mole of quarters, I would have 6.02 times 10 to the 23 quarters. So I have 6.02 times 10 to the 23 quarters. So now I need to convert that into a weight, right? Remember, each quarter is 5.67 grams, and I've got 6.02 times 10 to the 23 quarters. Right? I can use this in my next conversion because I want to go from quarters to mass. Well, I know that 5.67 grams per 1 quarter That's going to give me 3.413 times 10 to the 24th grams of quarters. Right, I've converted from quarters. Those units cancel out, and I'm left with units that I'm looking for, units of grams. Now the last step, I want to find that answer in kilograms. So my last conversion, 3.413 times 10 to the 24th grams. I know that I want to get rid of grams and I want to be left with kilograms. So I want kilograms up here. In 1 kilogram, I would have 1,000 grams. So that number would come down to 3.41 times 10 to the 21 kilograms of quarters. Right, we can do these calculations with things other than moles of molecules or elements, right, or atoms. We can do these calculations with things like quarters because 1 mole is just simply representing a number of objects that we have. And so again, dimensional analysis helps us just keep track of those units and make sure, right, the units are canceling out and that we're left with a number that makes sense for what we're looking for. As for significant figures, right, 3 significant figures here in the 5.67. That's our measured number. And so I would report the final answer to 3 significant figures. So 3.41 e to the 21 kilograms would be the same answer. So the important thing from this module, right, we need to know what a mole represents, right? Do not be afraid of the mole. It means the same thing. We use the mole in the same way we use something like a dozen. We also know Avogadro's number and how that relates to a mole, right? It tells us how many atoms or molecules we have in that sample. And we also want to be able to convert from moles to mass or mass to moles. Any of these calculations we've done, you should be able to go both directions. You should be able to calculate moles from mass or mass from moles. And now the last step we just did was now incorporating molecules or atoms. We should be able to go from mass to moles to molecules or atoms of the sample, depending on what we're talking about, forward or backwards. So that's what I would highly recommend, is practicing these calculations in both directions.